welcome. In this session, we'll recall some material on Taylor series of a function that has a scalar argument. Let's begin with supposing that f of t is analytic. And what that means is that it's infinitely differentiable and that the Taylor series converges everywhere. And the Taylor series is if we expand around some point that may be given to us, some point t0, that we can express f of any value of t as an infinite series. And what this looks like is this is the sum as I goes from 0 to infinity. So we have to remember about infinite series and convergence and so on. What we do is we take the ith derivative of the function at the expansion point and divide that by I factorial and multiply that by t minus the expansion point to the power I. So here it's important to observe that I here is an index variable. It's not the imaginary number. And another way that we can write that, so this is the compact series expression, we could also write that in terms. So for I equals 0, the zeroth derivative of the function is the function, and the 0 factorial is by definition 1, and any number to the power 0 is 1. So that is just f of t0. And then when we set I equal to 1, that will be f prime evaluated at the expansion point times t minus the expansion point, plus then when we set I equal 2, that is f double prime, the second derivative, at the expansion point over, and 2 factorial is just 2, times t minus the expansion point squared, plus dot, dot, dot. Now, this dot, dot, dot means that this is an infinite series. And so what do we do with this kind of infinite series? Well, the Lagrange remainder there are many forms of expressing this plus dot, dot, dot. There's a mean value, there's an integral term, and the one that we'll be using when we do use it, the one that we'll take advantage of, is called the Lagrange remainder. So the Lagrange remainder is for an interval that is either we might be approaching the point of interest from the left, or we might be approaching the point of interest, the expansion point, from the right, is for whichever interval we have, there exists a c in the interval such that the function with any scalar argument equals, we rewrite this, but now instead of infinite, what we're going to do is we're going to truncate it at k terms, and then the rest of the infinite series is called the remainder. So that is the sum as I goes from 0 to some value k of f to the power I evaluated at the expansion point over I factorial. So that part stays. And then the Lagrange remainder is this. We take the k plus 1th derivative divide by k plus 1 factorial multiply by t minus t0 to the k plus 1. So all of this looks like it's an extra term, but there exists a c in the interval where if we evaluate the k plus 1th derivative at c, we get an exact term. So what that's saying is that as we expand this, there's some value c kind of close to t0. Not necessarily exactly at t0, but something that's kind of close to t0, where we can express all of the remainder term. So what that means is that there are many kinds of remainder terms. What that means is that we get some kind of assurance for an analytic function that what we're losing has a certain bound. So we can put a bound on the amount of the remainder. There are two kinds of uses of this. So a truncation is where we take this infinite series and we stop evaluating it after a certain point. So in this case, we truncated at the value k, and then we had the remainder. And if we don't add the remainder, what we get is an approximation. So a linear approximation is one that's very, very often used. And in a linear approximation, what we do is we say f at any value of its scalar argument is approximately, so we use a weighty equal sign for approximately, is approximately the function evaluated at the expansion point plus the derivative at the expansion point times the difference between our point and the expansion point. So that's producing a linear approximation. Now you'll immediately realize that linear approximation and tangent lines are related. I encourage you to explore that further. A quadratic approximation is another one that is very useful in numerical optimization. And in a quadratic approximation, what we do is we truncate it after two terms. So we say that our function of a scalar argument is approximately, we take the function at the expansion point, we add the derivative of the function at the expansion point times the difference between our point and the expansion point, and then we add one more term, which is we take the second derivative at the expansion point, divide it by 2, and multiply that by the difference between our point and the expansion point squared. And so this is the full Taylor series. This is a truncated Taylor series with an explicit remainder. And then in linear and quadratic approximations, what we do is we just drop the remainder term and we approximate the function using a simpler function.